Curvature in normal vectors, Part 1. This parameterization orients the unit circle in a counterclockwise direction, while this one orients the curve in a clockwise direction. This one moves clockwise and starts at the top. Let's look at a parameterization of the unit circle where the object has traveled a distance of t units at time t. When time t and arc length s have the same value at all points, we say that arc length is the parameter for the curve. For this parameterization, I'd like to find speed. So first find velocity, and now your speed. The speed is equal to 1. Now that's very interesting. In fact, let R describe a smooth curve. The speed is equal to 1 if and only if time corresponds to arc length. This discussion motivates the arc length function. We use the definition of arc length to define the arc length function. As t increases, the length of the curve also increases. Now let's take the derivative of both sides with respect to t. What we get from the fundamental theorem of calculus is ds dt is equal to speed. Since the curve is smooth, this is a non-zero value. The arc length function gives distance traveled in time t. Its derivative is speed. If the speed is 1, then ds dt is 1, and the parameter t is arc length. ds dt equals speed. Let's talk about staircases. Spiral staircases. Let's talk about spiral staircases that go up. Consider this helix, that is, our staircase, where time is the parameter. Find the arc length function. This is what we're going to do. We're going to find velocity and then speed, and then we're going to use that to find the arc length function. You ready? Velocity, speed, clean it up, and we get an answer of 2 radical 5 for the speed. Use that for the arc length function, and we get that the arc length function is 2 radical 5t, linear, a linear relationship. Now, the parameterization we have been using uses time to give your position on the staircase. Find another description of the helix that uses arc length, that is, distance traveled, to give your position. When time was our parameter, we discovered its relation to arc length using the definition of the arc length function. This is what we got. Substitute t is equal to s over 2 radical 5 into the original parametric description. Do that now. Making the substitution, we find a description of the helix with arc length as our parameter. This position vector gives your position on the staircase when you have traveled s units. All right, let's change the subject. Recall that for a smooth curve, the unit tangent vector points in the direction of the tangent vector, r prime. By definition, its length is always 1, so the only way that the unit tangent vector can change is through a change in direction. How quickly does this change of direction occur? The magnitude of the rate at which the direction of the unit tangent vector changes with respect to arc length is the curvature of the curve. Curvature does not depend on the orientation of the curve, but it does depend on the shape of the curve. A large value of curvature at a point indicates a tight curve that changes direction quickly. If curvature is small, then the curve is relatively flat. The minimum curvature, 0, occurs on a straight line. With t as our parameter, arc length is a function of t. So we can write the derivative of the unit tangent vector with respect to time in this way using the chain rule. Now remember, ds dt is equal to speed. So we're going to take this equation, divide both sides by speed, and we get a new formula for curvature. And this is a great curvature formula to use, although I'll be giving you another one in the next video.